Good afternoon, everyone. I'm Xiaoniu from Shanghai Jiao University. I will introduce UGACHE, a cache system designed for embedding-based deep learning. Traditional machine learning can only handle dense, continuous input data. For example, the price of a product or the color of pixels in an image. However, in practical applications, categorical and sparse input can often appear. These sparse inputs usually appear in the form of a list of IDs. For example, in online shopping, the shopping cart contains a list of products represented by their IDs. Another example is the reference list of a paper in a citation network. These sparse inputs cannot be directly processed by traditional deep learning, so the embedding technique has been proposed. To enhance the model to be able to process sparse input, an embedding layer is introduced. The embedding layer converts such sparse input into a dense embedding vector that can be directly processed by the rest of the model. This figure shows an example of a recommendation model, which is typically used in online recommendation or click-through rate prediction. In the embedding layer, all possible embedding vectors are organized into a table. The input ID is used as a key to look up the corresponding embedding entries in the table. This process converts low-dimensional discrete IDs into high-dimensional continuous embedding vectors. For this process of extracting embedding vectors from the table, we call it embedding extract. In real-life applications, the range of possible ID numbers can be very large, even reaching billions. Compared to other layers that may only take up a few hundreds of megabytes, the embedding layer can take up to tens to hundreds of gigabytes. For current GPUs, the size of the embedding layer have exceeded their memory capacity. As a result, systems often store all the embeddings in the host memory. However, due to the limited PCIe bandwidth between the host memory and the GPU, extracting the embeddings becomes a bottleneck for the entire system. Thankfully, in embedding-based deep learning, there are often certain entries that are accessed more frequently than others. The skewness often comes from the preferences in user's choice and the parallel nature of graph. This skewness has been a common observation in various types of applications. Based on the skewness, some systems cache the hot entries into the GPU memory to address this bottleneck. But even with caching, embedding extract can still dominate the entire system. This is due to the poor cache efficiency and cache capacity in existing systems. In modern data centers, it is common to have multi-GPU platform with faster interconnects. The bandwidth between these GPUs is much higher than PCIe. These fast interconnects bring us the opportunity to unify the memory of multiple GPUs and create a larger and faster multi-GPU cache. In order to build a high-performance multi-GPU embedding cache, a system needs to address two key issues: the cache policy and the extraction mechanism. In cache policy, we need to decide how to place embedding entries on multiple GPUs. While in extraction mechanism, we need to efficiently use these fast interconnects to perform embedding extract across GPUs. However, we find that existing systems have deficiencies in both of these aspects. Regarding cache policy, several systems build a replication cache on the multi-GPU platform. These systems take the cache designed for a single GPU platform and directly port it to a multi-GPU platform. Therefore, each GPU independently caches the hottest embeddings. This causes a lot of overlap in the access load that can cover by the cache of each GPU. As a result, the fast interconnects on the multi-GPU platform is wasted. Recent systems build a partition cache on the multi-GPU platform. This system divides the hot embedding entries evenly to each GPU. Therefore, the cache capacity increases, reducing the miss rate. However, in partition cache, only a small portion of the cache hit requests are hit in the local partition, and most of the cache hit needs to be extracted from the remote GPU. Even though the bandwidth of the GPU interconnect is almost an order of magnitude faster than PCIe, it is still less than 1/3 of the local bandwidth. This causes the partition cache to bring only minimal improvement or even identical performance of our application cache. Therefore, in cache policy, we need to reasonably place embedding entries onto multiple GPUs and guarantees low miss rate and high local hit rate at the same time. Regarding extraction mechanism, recent systems uses a peer-based method to access embeddings across GPU. Modern GPUs have provided the ability to unify the address space of multiple GPUs, allowing GPUs to directly load or store memory addresses from a connected GPU. Therefore, system can directly load embedding entries from all other GPU in a zero-copy manner using a single kernel without the cost of buffering. However, we discovered that existing peer-based systems suffer from extremely low utilization of bandwidth. Cost of the low utilization is highly related to the way GPUs are connected. The topology of a multi-GPU platform can be divided into two categories, the hardwired and the switch-based platform. In the hardwired platform, GPUs are directly connected to each other. The bandwidth of each GPU is physically and statically divided among the links towards remote GPUs. Since the bandwidth is physically sliced, the bandwidth between single GPU pair is rather limited. However, during embedding extract, keys are randomly dispatched to cores in GPU. The random dispatch manner causes imbalanced use of interconnects. There can be certain interconnects that are congested by too many concurrent access, causing GPU cores to stall, while the rest of the links still remain underutilized. This causes low utilization of both the bandwidth and the GPU cores. Note that the same problems also exist on PCIe access. The switch-based platform, on the other hand, connects each GPU indirectly through specialized hardware like NVSwitch. Therefore, the bandwidth between different GPU pairs are dynamically allocated according to workloads. This seems to avoid the congestion. However, when multiple GPUs are accessing at the same time, the congestion can still occur. For example, when the first two GPU are simultaneously accessing the third GPU, due to bandwidth limitation on the third GPU, there will be collision between the first two GPU. This causes congestion similar to the hardwired platform, but in the cross-GPU scope. Therefore, in embedding extract, we need to avoid congestion, make a balanced use of interconnects, and improve its utilization. To address these challenges, we propose UGACHE, a multi-GPU cache system designed for embedding. UGACHE builds a static cache that targets read-only workload towards embeddings, such as GNN training and model inference like recommendation. UGACHE has two core components, the extractor and the solver. The extractor serves the embedding extract request from client, while the solver periodically provides cache policies. In extractor, UGACHE proposes a factored extraction mechanism. The meaning of factor is that we dedicate different GPU cores to access different links. Specifically, for each batch of embedding keys to extract, we first group the keys together based on their source location to read. Then, in each group, we dedicate specialized GPU cores to extract corresponding embedding entries. The number of cores is carefully determined with pre-profiled information about the platform. Therefore, congestion caused by too many cores accessing the same interconnect can be avoided. Note that this solution also works well on the switch-based platform at the same time. On switch-based platform, this method lets each GPU voluntarily uses only a portion of bandwidth of each remote GPU. Thereby, the congestion is avoided in a self-controlled manner without introducing explicit coordination between GPU. However, the factored method may cause GPU cores to idle. In each batch, the number of keys in different groups may not be balanced. This could result in erratic execution time for each group, causing GPU cores to idle and lower GPU's utilization. We notice that the local bandwidth of each GPU is strong enough to tolerate all cores performing extraction simultaneously. Thus, we use local extraction to pad this imbalanced remote extraction. We let each dedicated GPU cores to perform local extraction together after completing its non-local group. This can avoid the idle and ensuring GPU's utilization. Regarding the solver that provides cache policy, we noticed that existing policies are actually two extremes of redundancy in the cache. There's a trade-off in improving local hit rate and reducing miss rate. On the left side is the replication cache. In replication cache, the system replicates as many hot embeddings as possible. This can achieve better local hit rate, but also incurs high miss rate. On the right side is the partition cache. In partition cache, the system caches as many distinct entries as possible, thus sacrificing local hit rate to reduce the miss rate. To achieve optimal cache performance, there should be a sweet spot between these two extremes. The sweet spot should be determined by both the distribution of access frequency and the bandwidth and topology of the hardware platform. In UGACHE, we built a performance model and convert it into a mixed integer linear programming problem, or MILP. The solver takes the workload distribution and hardware information as input and outputs the plan for both placement and access. However, in the MLP problem, we need to make decisions for each individual embedding entries. Since the MLP is an NP hard problem, and the scale of embedding entries is too large, it is impossible to find a solution in feasible time. To solve this issue, we batch similar embedding entries together for solving. This reduces the scale of the problem from billion to 1,000, lowering the complexity. In practice, we can find a solution within 10 seconds. We further introduce hybrid granularity to ensure the accuracy of batching. This keeps the accuracy loss within 5%, and you can refer to our paper for more details. We evaluated UGACHE with rich setup, including all three mentioned platforms, 3 applications, and 3 datasets in each application. This figure shows the end-to-end performance for all evaluated workloads, ranging from low skill to high skill on different platforms. The replication cache and partition cache shows preferences on the workload with different skillness, while UGACHE consistently outperforms these two baselines. UGACHE also adapts to various platforms and achieves a considerable performance. Our factored extraction mechanism can improve the utilization of the bandwidth of fast interconnects between GPU and even PCIe. On the basis of applying the cache policy of UGACHE, this mechanism alone improves the performance by 1.6 times on average. We also analyzed the hit rate of cache policy solved by UGACHE on the different workload. When the workload is less skilled, to ensure low miss rate, UGACHE tends to build a cache policy similar to partition cache and results in similar performance. With highly skilled workload, UGACHE introduces more redundancy to improve the local hit rate. This can improve the performance while minimizing the impact on the miss rate. In summary, in this work, we first conducted a detailed analysis of multi-GPU embedding cache in terms of cache policy and extraction mechanism. We then proposed UGACHE to address these two aspects and improve the performance of multi-GPU embedding cache. Thank you for listening. We're happy to answer any questions.
Nicola? Okay, perfect. Go ahead.
Hi, I'm Saurabh from University of Wisconsin-Madison. You said somewhere that you're going to batch embeddings based on similarity. What sort of similarity metric are you talking about? Yeah. What do you mean by similarity?
Can you rephrase your problem? I know batch, but I don't know what your question is.
So you say batch similar embeddings. What
Yes.
is the metric for similarity?
The metric of, we define similar as the entries with similar hotness, i.e. access frequency.
So you would use an offline profile for this?
What?
Offline profile that you will already have?
Yes, yes.
Okay, cool, thank you.
Nice work. So GPU cache makes a lot of sense. I wonder if adding CPU memory as a cache can help this problem, or it's irrelevant.
Actually, we store some part of embeddings on the CPU. You can see our results here. The blue part is the access that are conducted from GPU accessing the host memory. But since the bandwidth is too slow compared to the interconnect, so we have to decide how many embeddings we should place on the host memory.
Thank you.
Go ahead.
Hi, this is Zhang from the University of Michigan. I have a question about the core dedication.
Yeah.
Honestly, before this talk, I thought it was impossible to use that kind of fine granularity. Even in the paper, you said that it is not possible, so you use the multi-process service for emulating or simulating that.
Yes.
But I still don't get how we can control that kind of granularity.
That's kind of tricky. We created multiple contexts in the same process. And there's API that CUDA driver provides that can limit the core usage of a single context. So we created multiple contexts with different limitations on the SM. And we launched different kernels using these different contexts in the same process.
So they limit the kernel to specific stream multiprocessor or cores
Yes.
within multiprocessors?
We limited cores. We limited kernels to so that it can only be executed on specific SMs.
I see. Thank you.
Okay, maybe I'll ask one last question. So I was curious if you've thought about potentially changing the scheduler as well, so that you're placing jobs that are more likely to hit keys locally instead of just remotely. I'm not totally sure how you would do this, but I'm just curious if you've thought about extending your work beyond just the cache, but also changing other parts of the...
I don't understand what the scheduler means.
Like where you're placing the kernels so that they're more likely to have higher hit rates, for example, of the local cache when you actually run. Maybe we should... Do you see what I'm saying?
So it's like dispatching requests to specific GPUs. So
Exactly.
Yes, it's discussed in our paper. We have a discussion, but there are actually several systems that have discovered this app, but they all require modification to the application. But we are more generous. Of course, it can be a future direction, and we are actually working on that.
Okay, thank you. Perfect. Let's thank the speaker.